Up to the duration of the course, we have looked at modeling of key inventory parameters such as safety stock, reorder point, reorder quantity, and so on. How to simulate them using version of Monte Carlo simulation stochastic approach. In this module, I would like to work on a technique called discrete event simulation, which is a popular modeling technique used to represent systems where changes occur at discrete points in time triggered by events. And it is particularly useful as a workaround for mathematically intricate problems. And it is very useful when we are dealing with any sort of queue in a process where entities enter the system and there is a resource which provides some sort of process to the entities and then they exit the system. So let's take a quick example. So DES will be very useful to model the scenarios as following. So for example, we have a random generation of customers entering a coffee shop, and these can be generated, let's say, based on a distribution. For example, let's say the time interval after which every other customer enters the process or the coffee shop is governed by some sort of mathematical model. Now this can be a complex model, or we can use a simpler mathematical distribution. So let's say this is following a normal distribution with certain mean and standard deviation, similar to the one we have seen earlier in this course. Next up, we have the coffee shop resource. Let's say this can be either the shop owner or some barista which performs a service for the customer. So for example, the customer enters the shop, orders coffee, gets the coffee, and then leaves the coffee shop, and obviously there will be a queue of customers at this point entering the coffee shop. So this whole series of events is actually a process which can be modeled very effectively using techniques such as DES. So basically, for resource, the resource will provide service also using a model, and it can also be a distribution. So for example, it will provide service based on an average time and a standard deviation. So for example, let's say this is another normal distribution which have mean and standard deviation, and this is based on the time it takes the customer to get the service from the coffee shop and then exits the coffee shop. So there will also be a waiting time period involved in the queue itself. And now let's see how does the program in Python will handle this. So if I take the most basic DES program, and I won't go into the details or more complex packages such as SymPy, but let's just take this small example. So to achieve this, we'll have an object created at the start of the program called environment, and this environment object will be like the master object which will handle the complete simulation which is being performed. And inside this environment object, we can have multiple sub processes running, like threads basically. So we can have, let's say, 2 processes running. In this case, it's a simple process, so it's just one process. But let's say we can have multiple processes running inside this environment, which will keep track of these processes, start the processes, and stop the processes as required. And as I mentioned, each process is basically like a big queue. So we'll have a large queue which will have entities flowing across this process, and this process will create something called as a priority queue, which is basically a data structure to keep track of all the entities which are flowing through this large queue. So underneath these processes, we'll have, let's say, entities, and then we'll have resources. And again, these are 2 distinct objects which this environment will create based on how we have programmed our environment. So let's say these entities will actually start creating customers, and this resource is basically going to model the coffee shop. So this will be, let's say, the coffee shop, and the entity itself will have its model, which I mentioned as a normal distribution with a mean and standard deviation, and also the resource will have its own model. with a mean and standard deviation. So typically speaking, once you run this simulation, the entities will start flowing from the generation part to the resource part. It will perform the action, let's say for the coffee shop, and then it will exit the simulation. So what we'll perform is an analysis on the waiting period of the customers in this case. It can also be on the time it takes for the coffee shop to deliver services to the customers, as well as how these two key objects interact with each other. So coming back to the topic of inventory, when we want to simulate this for the inventory, our entities can be the demand as well as the level of our stock, and we can have multiple processes running inside the simulation. For example, to simulate the ordering of the process, the lead time, the time it takes for the supplier to deliver us the materials, replenishment of the inventory, and so on. So basically, this will allow us to create a pretty dynamical inventory application using just a few lines of code. And finishing on the subject of DES, or discrete event simulation, so what are the main advantages? So firstly, it is providing a more simplified representation, because we are able to go directly from our flowcharts into this simulation instead of working out complex mathematics. It also provides us flexibility, experimentation, and visualization aids in terms of understanding our processes. Like I mentioned, the key components of DES models are entities, resources, events, for example, customer arrival, state variables like the queue length we just saw, flow of the program, flow, sequence and flow through which the entities move, the models, random distribution models, as well as the simulation clock, which the environment variable is responsible for. And generally speaking, the process for building a DES model is generally to define first the system, define its entities, resources, events, specify system boundaries and assumptions. Then we will look at our input parameters. We will define the distributions for those. We'll create the logic. We'll implement the model using tools such as SimPy. We'll run the simulations, and then we'll analyze the results. So we have covered the basics of DES. In this lecture, we saw how using this type of simulation we can model real-world processes, even processes which exist on flowcharts for us, into a kind of simulation, run it, and produce results.